Most of the sun's radiation reaches Earth in wavelengths within the visible spectrum. This is no coincidence. Our sense of sight evolved to be sensitive to this light. The sun's radiation passes through Earth's atmosphere, which is largely transparent to it, and is absorbed by land and sea, warming them up. These warm surfaces then radiate heat at longer wavelengths, known as infrared, which is invisible to the human eye. While nitrogen and oxygen in the atmosphere are transparent to infrared radiation, certain gases called greenhouse gases absorb some of this heat, trap it, and prevent it from escaping into space. Without this so-called greenhouse effect, Earth would be a frigid, uninhabitable ice ball. Water vapor is the most abundant greenhouse gas, accounting for about half of the greenhouse effect. Carbon dioxide is the second most abundant, playing a key role due to its chemical versatility. Thanks to its chemical properties, carbon forms more compounds than all other elements combined. All the molecules that make up living organisms, nucleic acids, like DNA and RNA, proteins, fats, sugars, etc., are based on carbon. There is plenty of carbon on Earth. Most of it, about 96%, is locked up in sedimentary rocks. The rest is found in the oceans, plants, animals, and soil, with only a relatively small fraction as CO2 in the atmosphere. Strikingly, almost all carbon transfers between the living as well as the non-living reservoirs take place in the form of CO2 via the atmospheric pool. The atmosphere is thus the central exchange hub of carbon. In photosynthesis, CO2 is converted to sugar, effectively removing it from the atmosphere. When living organisms metabolize this sugar, they breathe out CO2. Usually, this carbon cycle, the fixation of carbon dioxide by photosynthesis and its release through the metabolism of living organisms, is balanced, keeping its atmospheric levels relatively stable. However, this cycle can be disrupted. During the Carboniferous period, about 300 million years ago, a lot of carbon was fixed in vegetation and buried under conditions that prevented it from decomposing and being released back into the atmosphere. This carbon became fossilized as coal, oil, and natural gas. Over the past 2 centuries, humans have learned how to find, extract, and use this fossil carbon extensively, burning it to generate energy for industry and transportation. Carbon that has been sequestered over millions of years is now being released at an unprecedented rate into the atmosphere as CO2. This plot shows ongoing CO2 measurements from the Mauna Loa Observatory in Hawaii, started by Charles Keeling in 1958 and continued to this day by his son Ralph. The Keeling graph reveals how CO2 levels have changed over time. The annual zigzag is due to seasonal changes in plant growth and CO2 sequestration. Historic and prehistoric CO2 levels have been measured by analyzing air bubbles from ice cores extracted from glaciers, going back 800,000 years. From this plot, you can see how CO2 levels have skyrocketed in recent decades, reaching levels higher than at any point in millions of years. The oscillations you see here reflect ice age cycles, where CO2 fluctuated between 180 and 280 ppm. The last 10,000 years since the last ice age were exceedingly stable. During this period of stable climate, human societies and technologies advanced from the Stone Age to the 21st century. Our climate is directly affected only by atmospheric CO2 and not by carbon in any other form. Given that only a tiny fraction of Earth's carbon resides in the atmosphere, one might expect atmospheric levels to be buffered against rapid changes. This is indeed the case, and I will explain in the following video how this buffering takes place. This buffering is, however, much too slow to effectively offset the current CO2 surplus we are generating. Even if all the excess CO2 we are releasing into the atmosphere eventually ends up in rocks, this will take millions of years. In contrast, if we burned all the coal on Earth at the current rate, CO2 concentrations could rise to 10 times their current level. It is important to note that greenhouse gases include more than just CO2. Human activities also release potent greenhouse gases like methane and nitrous oxide. Although their concentrations are lower than CO2, their relative warming effects are much stronger. Burning fossil fuels for electricity generation accounts for about 25% of human greenhouse gas emissions. Agriculture and land use account for another 25%, and industry adds 21%. while transportation contributes around 15%. These sectors, along with solutions to mitigate their impact, will be explored throughout this course. Addressing greenhouse gas emissions requires a multifaceted approach. There is no single solution. However, this diversity of challenges also offers many opportunities for action. Project Drawdown, a leading resource for climate solutions, has compiled a list of proven strategies to reduce emissions. We will revisit some of these solutions later in the course.